After integrating out the high energy mode for a system of cold atoms, we ended up with a Lagrangian for a massless Goldstone mode. We can rescale the field to end up with a more familiar form for this Lagrangian. This Lagrangian exhibits similarities with the Klein-Gordon Lagrangian for a massless field. If we restore C and H bar, and if we plug in this Lagrangian into Euler-Lagrange equation, we see that we get a wave equation with the speed of the wave equal to c. And the corresponding particle has an energy, which for a massless field, by analogy we see that our effective Lagrangian for the Goldstone mode describes a massless field, which in the classical limit gives a wave equation with a velocity, and thus an energy. This equation relating the energy with the momentum is called a dispersion relation. Usually for a non-relativistic field, the dispersion relation gives us an energy which is quadratic with the momentum. But now for cold atom with a repulsion, spontaneous symmetry breaking gives us a dispersion relation which gives an energy which is linear with the momentum. This difference is what explains the superfluid behavior. Superfluidity is characterized by the motion of a fluid which is without any viscosity. And viscosity is produced by the collision of the particles in the fluid, which lead to a dissipation of the collective kinetic energy into internal heat, internal excitations. If we consider a normal non-relativistic field with an energy which is quadratic with the momentum, because of the finite volume we have a discretized set of momenta. We see that at low energies there is a lot of possible available states to the particles. This large level density at low energy makes the collision very effective to dissipate collective energy into internal excitations. However, in the case of a superfluid, we have an energy which is linear in momentum. This strongly reduces the number of available states for the system. As a result, when two particles collide, they are not as likely to find an available final state to populate. Therefore, this makes the collision less efficient, and as a result, that reduces dissipation and produces superfluidity. Manifestations of superfluidity are quite remarkable, with superfluid going through the bottom of a bucket or climbing up its edges to escape.